Okay, so this is my second video in my vector calculus playlist here. In this video I'm going to show you guys how to derive the formula for finding arc length, and I'll just do this example here where my position vector is parameterized. It's defined by this parameter t here, and we're going to try to find the length of the arc as t varies from 0 to 1. Okay, so you can see here that when t is 0, you're at the point 1, 0, 0. So here's our position vector for t equals 0. And then you can see that at t equals 1, you're at the point 1, 1, 1, which is like somewhere here. So our position vector does something like that. So as you can see here, this is linear in terms of t, so it's not a line like we did in the first video. It's actually some kind of curve. It actually looks like it increases faster in the z direction, so it doesn't really matter what the curve looks like. All we know is that it goes from this point, does something, and goes to this point here when t equals 1. Okay, so I'm going to zoom in on a little... Oh, before I do that, as you can see from this vector equation here, t is always 1. Okay, so this curve actually lies on a plane that intersects the x-axis at x equals 1 and is parallel to the yz plane. So this curve lies in a plane that's parallel to the yz plane at x equals 1 here. So that means that if I zoom in on a little segment of the curve here, so let's say the curve does something like this. And I know that I didn't talk to you guys yet about tangent vectors, but you can imagine that if I have some vector that to the curve at this point here, hopefully you can see that the component in this direction is going to be well, in this case delta y, because this is in the direction that y changes, and then my vertical component here is in the direction that z changes, so it's going to be delta z. And hopefully you can see that, like, if I want to find the length, call it delta L, of this little segment here, just by Pythagorean Theorem here, it's going to be dy squared plus dz squared, like this. Now, if I multiply this side of the equation by delta t, and I bring the denominator delta t underneath this radical here, that means that my little differential length element here will look something like this. Now you can see that I can let t vary from 0 to 1, and if I sum up all of these little differential elements along this length, then I will get the length of this curve from when t equals 0 to t equals 1, something like this. Okay, so this is pretty easy to understand, although you've never seen tangent vectors like this before, but conceptually it's pretty intuitive. Okay, so what are these things here? Well, dy dt, that's, from first year calculus, that's the rate at which this curve changes in the y direction here. So this is the, the y component of this position vector. So that means that I can differentiate this component here, plug it in there. dz dt is how fast it changes in the z direction, so I can differentiate the z component, plug it in here, and then I just have a straight up integral, and find my answer like that. Okay, so let's do that. Okay, so dy dt, the equation was, the vector equation was this, I think. Yep. Okay, so let's differentiate it with let's differentiate the y component here. So you have 2t squared. We'll differentiate the z component, so we'll have 3t squared dt. Okay, so then we'll just work out this standard integral. So we'll have 4t squared plus 9t to the power of 4. Alright, we can factor out a t squared there. So we'll have 4 plus 9t squared all multiplied by t squared. But since it's the square root of that, the square root of t squared will end up being t outside of the radical here, like this. So we end up having something like this. Okay, so if we were to put this back inside under the radical, we would square it underneath the radical and multiply it against this guy. So we'd have t squared times t squared is t to the power of 4, and then t squared times 4 is 4t squared. So hopefully I didn't lose you there. Now, didn't mean to put an equal sign there. Now you should recognize that this is, if you try to integrate this, it's sort of tricky, and I could admit that I sort of looked at this at first and was like, holy, what, is this some sort of perfect square here where I can simplify it somehow? But no, actually you should see that you have something underneath the radical here with a t squared in it, and then you have part of its derivative outside of the radical here. So that should be a little clue that you should do some sort of u substitution. So if I let u equal 9 times t squared plus 4, then that means that delta u is going to equal 18t dt. So this greatly simplifies this integral, and I end up having, we'll worry about the bounds of integration in a minute here. So I said that underneath there we have u. Now we have t dt, and right here we have t dt. So that means that wherever you see t dt, you can replace it with 1 over 18 du. Now we just have an integral in terms of u here, and we know that when, to figure out the bounds of integration here, when t is 0, you can see that u is going to equal 4, and when t is 1, u is going to equal 13. So this is how I always do my substitutions like this. I do my bounds right away. I don't substitute back in terms of t later. I just leave it all in terms of my new variable, and solve it like this. So anyway, so if we integrate this, this is u to the 1/2. So when we add 1 to that, we get 3 over 2. When you evaluate this at u equals 4 and u equals 13, like this. So if we differentiate this, the 3's will cancel out, the 2's will cancel out, we'll have a half here. So we have this guy again. So this is going to end up being 1 over 9 times 3, so 1 over 27, and then inside I'm going to have, plug in my 13 for u, and plug in my 4 for u, and then I put this in my calculator, and it equaled something like 1.4. Okay, so that's your final answer. So that means that the length of this curve from this point here to this point here is approximately 1.44.